Okay, so I've got a cable B that's pulled down at 4 feet per second and a speed that's decreasing at 2 feet per second squared. Now I want to find the velocity of block A. Now the easiest way to treat these is to basically find the total length of each cable, okay, relative to the moving pieces. And I'm going to base everything on the center of some of the pulleys there. Okay, so for example, from here down to the center of this guy, we're going to call that um, the position of pulley A. Okay, and to the center of C here, we're going to call that um, S sub C. Okay, then we will define this position as the position of the end B. Now, there's no pulley there, but that end is moving, right? And it's going to be moving independently of C and A, right? Okay. And the last thing I'll do is I'm just going to give the entire height here an H, like so. Okay. So that gives me the center of the pulleys that I can then define. So I'm going to start with that top one. And I'm going to find the length of that cable. Now, there's some pieces of the cable, for example, right here, right? There's that piece of cable that, isn't from where that pulley is. But this doesn't change, okay? But we're going to give this a value that I'm just going to call y, right? Okay, so I've got y, and then I've got plus SA, right? Going from y, then SA. Now I've got this piece that goes over the pulley, like so. And we're going to call that a value of x, okay? So plus x. And I'm going to treat every piece going over the pulley as that same x. So now I move back up here, another SA. Then it goes over a pulley, like so. That's another x. And then finally, this goes down a point SC. So that is the total length of that cable, okay? So that gives me the length of the cable. Now, what I want to do is I want to take a time derivative of that, okay? So I'm going to take the time derivative of that cable, okay? Well, that cable does not change in length. So when I take that time derivative, L1 becomes 0. Or I should say the time derivative of L1 becomes 0. L dot is 0 because that length can't change, okay? It's not an extendable cable. Okay. The other thing that can't change is y, right? That little piece of y up at the top there, that doesn't change as time goes on. What does change is the position of those pulleys. So SA, okay, a time derivative of position becomes velocity, okay? The cable over the pulley stays constant, right? The pulley stays the same size, so it's basically half of the circumference, doesn't change as time changes. So those x's all go to 0. SA goes to 0. I'm sorry, SA goes to VA, X goes to 0, and then SC becomes VC. Now I can simplify this a little bit, and I can say, okay, from that I say 0 equals 2VA plus VC, okay? Now, very easily, I can go from that to acceleration by taking another time derivative, which becomes very simple, right? Because all the V's just turn into A's, okay? So 0 also equals 2AA plus AC, okay? But I've got this second cable, that cable on the bottom that I'm also going to do. So let's go ahead and take a look at that. So again, I've got uh, from the ground up to the pulley at C, which is going to be H minus SC, right? That's that length of cable, okay? Plus an X, which again is the piece of cable over that. As we move through, you can probably drop this off because we know that's always going to take a time derivative equal to 0, but I'll include it for right now. And then that last piece of cable, which would be between C and B, is going to be SB minus SC. Okay. Taking a time derivative of this, again, the length of the cable can't change with respect to time. H can't change with respect to time. So I get negative VC, X doesn't change with respect to time, plus VB minus VC. And then from that, I can find, okay, well then 0 equals VB minus 2VC. Similarly, AB minus 2AC. So now I've got equations that relate velocities and accelerations of all of the moving pieces, A, B, and C. Okay, so what I'm trying to find here is I'm trying to find the velocity of A. Okay, and what I know here is that the velocity of B, okay, what I know is that the velocity of B equals 4. Now, that's downward, but when I think about it, it's actually going to be a positive VB because SB is going to increase in size, right? As this gets pulled down, SB will increase in size because my 0 is at the top, right? So I'm going to call that a positive VB, okay? So from that, I know then that VB4 equals 2VC. So VC equals 2. Okay. The fact that that's positive also makes sense because as I move down with this, right, VC is also going to move down, thus increasing SC. So VC will be a positive value as well. I'm going to take that, plug it into the equation at the top where I get 0 equals 2VA plus 2. From that, I get VA equals minus 1. Now, what minus 1 means is VA, or I'm sorry, SA is actually shrinking, right? For SA to shrink, that means it's actually moving upwards, which I think makes sense that A is going to be moving upwards. So I would write that as 1 meter per second upward. So you have to be careful with your positives and negatives to get those to all work out. Now I'll do the exact same thing here with the acceleration. The difference here is now the speed is decreasing. So everything gets flipped. Okay. So what I have here is 0 equals AB, which I'm calling negative 2 now, right? Because it's decreasing in its speed. Okay. Minus 2AC, which from that tells me that AC equals negative 1. Plugging that into the equation above, I get 0 equals 2AA minus 1. From that, I get AA equal to 0.5. Okay, but again, positive because my 0 is up at the top. Positive actually flips that. So instead of, positive upward, we're going to call this meters per second, and we're going to call it downward in the other direction. Okay, so that's how you deal with these cables. You find the length of the cable and then take a time derivative knowing that the length of the cable won't change with time. So the time derivative of the cable will be 0.